Our speaker of this talk is Andrea Montanari. He's a professor in electrical engineering and statistics at Stanford University. And the title of his talk is Statistics and Computation in Graph Estimation Problems. So thanks.
Okay, yeah. So thanks for the kind invitation. And yeah, so I actually prepared 2 talks for this presentation, 2 different presentations, because I was uncertain until the last moment what to give. Because I gave the same in MIT 1 month ago, so if any of you was there, please leave the room. Okay, but then I decided to give it anyway. Okay, so what I'm going to talk is actually 2 very simple graph or matrix estimation problem. So here matrices will be 0, 1, and symmetric, so they can be thought as graph. But you know, pretty much everything generalized to other matrix ensembles. So the first problem is, let me call it the hidden subgraph problem. So here you generate a random graph over n vertices as follows. You know, you select a subset of k out of the n vertices arbitrarily, and then you connect any 2 vertices inside this k with probability p. Okay? And then for any other pair, you connect them with the probability q, where q is strictly less than p. Okay? And actually often, you know, actually the most studied case of this problem is the case p equal 1 and q 1/2. So the background is just uniform, and the subgraph is a clique, is a completely connected subgraph. So this is why it's called the hidden clique problem. So edges are conditionally independent given the set S, the unknown set S, with these edge probabilities. Okay, and of course, the problem is to identify the set S, but okay, how many of you can see the set S in this case? I can see it. Yeah, in reality, the entries are not colored and they are not ordered. Okay, and the other example is the hidden partition problem. Here I generate a graph with 2 subsets of n over 2 vertices. So I partition it arbitrarily in n over 2 vertices, and then I connect any 2 vertices inside each side of the partition with probability p, and across the partition with probability q less than p. And the problem is to find the partition given 1 realization of such a graph. And of course, the entries are not colored and they are not ordered. Right? So these are two very simple problems to state. This is why I like giving this talk. These 2 problems look very similar the first time you hear about that. There is some p and some q, and then some graph, and then you want to identify some set of vertices, right? So they look very similar, and the first intuition is that they should behave similarly. And here I will be looking at these 2 problems, but from a point of view of detection, and more precisely detection threshold. Okay, and so the question is, under which condition I can identify such a structure and identify the presence of such a structure and distinguish it from the null model in which each edge is present with the same probability. Okay, so of course the problem becomes easier when p and q become very different, for instance, or when the subset in the first problem becomes very large. And the problem is understanding under which condition you can distinguish these graph models from the purely Erdős-Rényi random graph. And in this question, there are 2 kinds of thresholds one should distinguish. One is a classical statistics or information theoretic viewpoint. And the question is there any algorithm that will find such structure? And the other viewpoint is, let's say, more computationally, and is there a polynomial time algorithm that identifies such a structure? Okay, and blurring over a number of details, if you want to get the overall picture of this area, this is the situation. The 2 problems behave very differently. For the hidden partition problem, there exists a threshold that is when the ratio of p minus q over square root of 2p plus q is bigger than 1 over square root of n. This is the information theory threshold, and this is meshed computationally. And for the hidden subgraph problem, the situation very different. You can find the subgraph as soon as this is larger than 2 log n, basically. So this can be extremely small, and still you will find it. It's very easy to see this thing. And instead, despite 30 years of research in this problem, there is no algorithm that finds it in polynomial time unless the size is bigger than square root of n. Some constant times square root of n. Okay? Okay. And this really summarized lots of research. In the case of the hidden subgraph, dates back to work by Jerome in the early 90s, who defined the problem and showed that basically MCMC cannot find the indent click when this is too small, and there is a long sequence of work that first proved the algorithm that achieved that, and then proved converses. Okay, and I'll cite some of these works later. In the case of the hidden subgraph, dates back again to the 80s, where people introduced it and proved the first achievability results. There has been a recent upsurge of interest after work by physicists, in particular Florent, Lenka, and others, and then all the way until now. Okay, and the big picture that emerges from this research is the following: that if you want to determine this statistics threshold, is there any algorithm that finds this structure, that detects this structure, then there is very good mathematical tools to understand this question, to answer the question. It's relatively easy to find out whether this can be done statistically. There are much fewer tools to understand whether this can be done in polynomial time. Okay? And if the two type of thresholds were the same, then this would not be a big deal. But these two examples show that they can be very different. In particular, for the hidden subgraph model, the computational constraint is much stronger than the statistical constraint. Okay? So lower bounds that come from requiring the existence of a polynomial time algorithm seem to be much stronger. All right? And there is not really a lower bound. Okay, so in this talk, I want to describe a generic tool for computational threshold that for bounding computational threshold that has emerged within the theoretical CS community, and we kind of got interested in this recently. Okay? So I'll describe this general idea very briefly, and then I'll describe how this applies for the hidden partition model and then for the hidden click problem, and then I'll draw some conclusions. All right, so the general approach, okay, so what is the basic problem here? The basic problem is proving lower bound, that is proving impossibility results, proving that no polynomial type algorithm is able to do this and this. Why this is a difficult problem? Because while the standard way to prove computational hardness is reduction, you prove that essentially something is at least as hard as satisfiability. Okay? So in this kind of problems, reduction doesn't work very well. It's not easy to make it work for two reasons. First reason is that there is not a good complete problem, like satisfiability, that is very close to many other problems in a sense, very easy to reduce from. And second point is that probabilistic models are fragile to reduction. When you do reduction, you reduce in worst case, and worst case is very robust to reduction. But average case is very fragile to reduction. The distribution of the instance changes a lot when you do a reduction, of course. All right? So there are exceptions to this thing. In particular, started with work by Bertin and Rigolet. People proved the reductions for sparse principal component analysis, from hidden click to sparse principal component analysis. So these are interesting line of work, but they are reduction between problems that are very close to each other in a sense. Okay. I'm going to talk about the complementary approach that is analyze SDP semi-definite programming hierarchies. So this is a new approach in quote unquote because it really dates back to the early 2000s with groundbreaking work by Feige and Krautgamer and others. In particular, this paper proved that a certain Sdp hierarchy, the Lovász-Krivers hierarchy, was unsuccessful in solving the hidden click problem. Okay? But this approach took off late 2000, and due to a large extent to people that are not far from here, Ankur, Boaz Barak, and others. Okay? And these works actually take a specific sequence of Sdp hierarchy that is the sum of square hierarchy that is very interesting in itself. Okay? So I'll describe this SOS hierarchy in two specific problems, in this, two specific examples. I will not give a definition in general, but at a high level you can think of it as follows. It's a black box in which you input an instance of your problem. So in our case, it's a graph G and an integer D, and this spits out a number. The number is solution of some optimization problem. And the important facts about this algorithm, this is an approximation of some combinatorial problem that you want to solve, but it can be computed in polynomial time as long as the degree is finite, is bounded. Okay? So as D gets larger, this gives a sequence of approximation that is tighter, but is more complex to compute. And the more you think about this black box, once you understand it, the more it's difficult to come up with ideas that are better than it. Okay? So this has led some, theoretical computer scientists to conjecture that this is conjecture, or suggest that this might be for some problems the ultimate algorithm. And the sum of square hierarchy really was present in Russian literature since the 80s, but really took off since work by Lasserre and Pablo Parrillo in the early 2000s. Okay, so I'll describe this in these two cases. So I look at either level 2 or level 4. So the very first few levels, normally you take even degree. It's just simpler to think of it even degree. Okay, so I'll look at the hidden partition problem first. So again, this is the problem. You have n vertices partitioned on two subsets of n over 2, denser edges inside, weaker edges across, and of course they are not there, the red. And formally what I'll talk about is the hypothesis testing version of this problem. Okay? You can formulate it, formalize it in many ways, but this is one possible way as a hypothesis testing problem where you have two possible distributions. Under hypothesis 0, P0, all edges are present with the same probability independently. Under the alternatives, edges that are within each part of the partition, each side of the partition, are present with a slightly larger probability than the others. Okay? And here I set the edge probability to be constant over n, scaling like 1 over n, simply because this is the most difficult regime. Okay? So is the model clear? All right. Okay, so the first question is, what is the information theory threshold? That is, under which condition on this A, B, and n you can find actually, you can distinguish. What we want is to distinguish between these two distributions with high probability. That is, to have a test that fails with probability going to 0. And this question was settled by Helkanen, Mossel, Joe Niemann, and Alice Lai a couple of years ago, and they proved that there exists a test that succeeds without probability if and only if this ratio a minus b over square root of 2a plus b is bigger than 1. This ratio makes perfect sense, right? A and b are the average degree of a vertex, the average number of friends of its own type and on the other type. So this is the difference of the 2 degree. A square root of a plus b is roughly the standard deviation of the degree. Okay? And this proves a conjecture, actually, by a very beautiful conjecture by statistical physicists. The situation is more, took more time, or it's more complicated mathematically for settling from a computational perspective. Earlier work was by Friese, Dyer, and Karp and prove that basically if P and Q are distinct, then you can find the partition asymptotically. But again, the question was settled by Mossel, Niemann, and Sly, and independently by Laurent Massoulier, and proved that the necessary sufficient condition is again the same. Right? So there is no gap between these two methods. I mean, these two thresholds, information theoretical and computational threshold. Okay, so if you read these papers, you realize that these papers all use very ingenious algorithms. These are very smart people that looked very, closely about what is the properties, what are the properties of these graph models, and try to extract properties that allow to distinguish between these two models. Okay, so this begs the question, what if I'm not ingenious, right? This is not just an academic question. First of all, I'm not ingenious. And second, you would like to solve these problems with methods that are somehow robust, that are generic. Because after all, we know that the model is wrong, right? No real data set as this model. Right, so if I'm not ingenious, the first thing that I do is maximum likelihood, right? So you can encode the partition with plus or minus 1 variables, plus 1 on one side, minus 1 on the other side. So what is maximum likelihood? If you think 5 minutes, or you can give you as an exercise to an undergraduate student, found out that maximum likelihood does the following: maximizes the number of edges on each side of the partition, subject to the partition being equal, balanced. Okay, so if A is the adjacency matrix of the graph, you can write this in this way: you maximize sum over I j, indicator function of xi xj subject to these constraints. Okay, you can rewrite this very easily, as a polynomial in xi and xj in this way: sum over ij xi xj. This differs from the previous objective just by additive constant and a multiplicative constant. Okay? So you maximize a quadratic form subject to a linear constraint, this plus minus 1 constraint. Okay? Now I want to get rid of this constraint. So what I'll do is that I'll add a Lagrange multiplier that is a constant times the square of sum over I xi. Okay? Now, if this gamma is very large, this term, this constraint term, this soft constraint, will force actually sum over I of xi equal to 0. So this problem is equivalent to the previous one. Turns out that actually the good value of gamma to put here is A plus B over 2. You'll see why in a second. So I have this now very simple problem. I have a quadratic form with binary constraint. Okay, let me rewrite this in vector form. I can write x as this as xx transpose times the matrix A minus expectation of A. You see, gamma over n is the expectation of any of these entries under the null model, under the model where each edge is present with the same probability. So what I'm doing here, I'm subtracting from A's expectation. And this is the ordinary scalar product between matrices, trace of AB transpose. Okay, so this is a very neat formulation. Unfortunately, this problem is NP-hard. Okay? So what is SOS2 is, SOS is a sequence of relaxations, and SOS2 is a very simple convex relaxation to this problem. So it gives an upper bound to the value of this problem. Okay, so how the relaxation works is very easy. You replace this by a matrix capital X, and you impose two constraints that X is positive semi-definite, because this has to be positive semi-definite, and the diagonal terms are 1. Okay, now my test will be the following. I'll compute this value. I can compute it in polynomial time because it's a convex, it's a semi-definite program. And then I'll output 1. So what I would have done if I had computed, I was able to compute the maximum likelihood. Well, the maximum likelihood test would have been if the value is larger than a certain threshold, I'll say the alternative is true. If it's smaller, then the null model is true. And I'll do the same here with the relaxation. If the value of the relaxation is above a certain threshold, I'll say 1. If it's below a certain threshold, I'll say 0. Okay? And you know, let's not fuss about the threshold. I could have given you a formula, but you know, that's not the point. Somebody will give me a value for the threshold. Okay, so you know, okay, it took us a few slides to derive this relaxation, this method, but I hope I convince you that this is not an ingenious method. This is really off the shelf. It's something that you know, people, master level students in engineering know how to do. You know, it's an easy homework. It's not a difficult homework. And the question is really how well does it work? Okay, and the result is that it works pretty well. So this is a theorem with Subgraph Sen, who's a student in statistics in Stanford. This test works with high probability if this magic ratio is bigger than 2 plus a little bit. A little bit is small law of a plus b, of 1 in a plus b going to infinity. So we're thinking of large but bounded degree. And when the degree is large but bounded, this method is suboptimal by factor 2 at most. Okay, so this is suboptimal at most by factor 2. Under a random matrix condition, these 2 should go to 1. Conjecture. So I can explain you conjecture if you want at the end. So the real value here should be 1, but we cannot prove it at the moment. There was work by Guédon and Vershinin on the same kind of method, and they proved the same result with a slightly weaker constant. And finally, okay, the same method has been studied by Emmanuel Abbé, Afonso Bandera, and by Bruce Hayek and others, but their work is in a pretty different regime. Okay, so this is a theorem. One might wonder, okay, this factor 2, I don't like it. It's really plus this small law of 1. So this is not really an optimal method, etc. If you do simulations, this is actually this is the information theoretic threshold, so here we look at graphs of increasing size at average degree 10, so a reasonably small average degree, and this is the information theory threshold. As soon as you go above the information theory threshold, the accuracy in reconstruction becomes strictly positive, strictly bigger than 1, and not going to 0 as n goes to infinity. So this method basically, in practice is essentially optimal, and as I said before, this is really off the shelf. Okay, there is actually one theorem that I like in this work, and is really the key technical theorem, and I like it because it's sharp. It makes you understand why this works. And the key technical ingredient is a sharp characterization of this semi-definite program under the pure Erdős-Rényi graph. So now you take a pure Erdős-Rényi graph, Gn gamma over n, so edge probability gamma over n, and you ask yourself, what is the value of this semi-definite program? So to put this in context, let me try for a second to relax further this program to get an upper bound. So SOS2 is upper bounded. You can remove the xii equal 1 constraint and replace it by trace of x equal n constraint. Okay, this is a further relaxation, and the value of this relaxation is basically the largest eigenvalue of the adjacency matrix, the largest non-trivial eigenvalue of the adjacency matrix. Okay, so you get this upper bound. This is upper bounded by the largest eigenvalue of the adjacency matrix minus its expectation. Okay, so this would give also a spectral method that is decide on the basis of the largest eigenvalue of the. Now, if you look at the largest eigenvalue of a sparse graph, this has a very annoying way of behaving. If the degree is some polylog, so this sticks together theorems by Krivelevich and others, and Sudakov and by Wu for the large degree. So if the degree is larger than some log polylog factor, then the largest eigenvalue is very large, diverges with n. Okay, it's 2 square root of log n over log n. So it's no. If it's order 1, it's very large. It's 2 square root of log n over log n. Okay? So this comes in because there are vertices with a very high degree, and the corresponding eigenvector is basically the unit vector concentrated on those vertices. So this is a well-known fact. If the degree is large enough, instead you have the Wigner kind of heuristics comes in. The largest eigenvalue is 2 square root of gamma of the average degree. Okay. Now the interesting, so this implies in particular that the spectral method will not work if the degree is not bounded. It's bounded. So this is an illustration for some sides. This is large degree. You follow very well the semicircle law. Small degree, you don't follow it at all, and actually you have Lifshitz tails that extend to infinity. So this is the theorem. If you take the same Erdős-Renyi random graph, and now you do the SOS instead of doing the spectral relaxation, you get a value that is 2 square root of gamma plus small of square root of gamma. In other words, what happens is that when you look at largest eigenvalue, this behaves badly because it gets an eigenvector that is completely localized. Okay, and completely localized eigenvector are not nice. Now, what the Sdp does is that it forces the eigenvector to be completely delocalized in a sense. And once you force this, then you get exactly the Wigner edge. Right? So this discontinuity is eliminated. All right. Okay, so what I like about this theorem is that there is an equal, not a bound, of course. Okay, so the proof idea is, relatively simple, but it's something that is not done in combinatorics. We analyze first the GOE, an analogous problem, this Sdp for the GOE and ensemble, so Gaussian random matrices, and then we use Lindenberg method to translate this in a result for graphs. Okay, second part, now if you got a fell asleep, this is hidden click. So now we are going to a more powerful relaxation that is the fourth level of the hierarchy. So again, the situation here is that you have a subset of vertices that form a clique, and each other pair is connected with probability 1/2. And you want, again, let me state it as an hypothesis testing. The hypothesis 0 is that every edge is present with probability 1/2. The hypothesis 1 is that there is a set where each edge is present with probability 1, and outside they are present with probability 1/2. Right? So now the information theory threshold is very easy to understand. This is basically a random graph result that date back to Grimmett in the 70s, and was generalized and studied in every detail by Arias Castro and Verzelen. And the result is that you will, specialized to this case, you are able to find the clique with high probability by exhaustive search if the clique size is bigger than 2 log n. And the 2 log n comes because this is basically the size of the largest clique in a GN 1/2 random graph. Okay, as for computational thresholds, the situation is much less, much bleaker. the simplest possible algorithm that you can think of is you just count the number of edges in the graph. If you planted a click, probably there is a little bit more edges. So you count how many edges. If it's above a certain threshold, you say there is a click. If it's below that threshold, you say there is no click. So this works if the size of the click is bigger than square root of n log n. Okay. Now, the best algorithm that we know of basically is a spectral algorithm by Nogalon and others that will find the click as soon as k is bigger than a small, arbitrarily small constant times square root of n. So in time that n to the log of 1 over epsilon, basically. And there has been a lot of papers since then, but very little progress on this specific question. Right? So again, I'll give you an optimization formulation. What is the optimization formulation? You can write the size of largest click in this way. You maximize the sum. You have 0, 1 variable xi that indicate whether vertex I belongs to the click or not. And you maximize the sum over the xi subject to xi in 0, 1. And every time that ij is not in the click, is not an edge, I say xi xj equals 0. Why? Well, because if I and j are both in the click, so if this problem is 1, then the edge ij must be there. Right? So this is just a contrapositive. So this is formulating the problem as an integer programming problem. And now we'll go about relaxing it. This integer programming problem is, of course, NPR. Sdp SOSGD is a semi-definite program with n to the d variables. And intuitively, what it does is that it captures all correlation of up to d variables. Now, one way to think about convex relaxation is that instead of solving for integer variable, finding a deterministic assignment of the variable, you are trying to find some sort of distribution over the xi's. Okay? This can be made more precise, but I don't have time to do so. But in this spirit, the SOS, instead of finding a distribution, it finds moments of level up to d. All right, so I need a piece of notation. So now I'll define the SOS d. So this is probably the most interesting part of the talk if you never heard about it. So a piece of notation. I'll denote in this way the set of first n integers. And this way, the set of subsets of that set of sides at equal to L, and this is of sides at most L. So the SOS is just a convex problem that has decision variables as a function from this sets of sides at most d to 0, 1, the interval 0, 1. Right? So for any such set, I get a number x of s. Right? Now, this is a function, but since it's a function of a finite space, it's really a vector. And it's a vector of dimension n to the d, roughly. Okay? So this will be my decision variable. It's useful to think of what is the interpretation of this decision variable, because this then helps understand the relaxation. You can interpret x of s in a sense as the probability that s is in the click. So this is not probability with respect to random graph. It's probability with respect to convex relaxations. And out of this x of s, I construct a moment matrix that is indexed by subsets of size at most d over 2, whose entry s1, s2 is simply x of s1 union s2. So according to this interpretation, it's just the probability that both S1 and S2 are in the click. So in this sense, this moment matrix is a matrix of correlations. Okay, so what is the relaxation now? So this is my integer program, and this is the relaxation. What I do, I maximize the sum over I of x of I. Now, what is this? According to my interpretation, this is the expected size of the set. Right, so I want a set of maximum possible size. And then x of the empty set is 1. Oh, why? Yes, because the expectation, no, the probability that the empty set is in the clique is 1. Empty set is in every other set. The moment matrix has to be PSD, because every moment matrix is PSD. And then every time GS is the subgraph induced in G by the set S, is not a clique, then S to be 0. This is x of S has to be 0. This is the only problem-specific line. Right? So this is saying every time GS is not a clique, S has 0 probability to be in the big clique, right? So this is the relaxation. And this is, of course, convex. It's a semi-definite program. Okay, now, again, the first time you hear about it, this sounds very strange. But the more that you think about it, more is natural. And it's, again, not taught to master level students, but you know, it's really off the shelf again. You know, you spend perhaps half an hour learning this, and then you can do it, you know, with eyes closed. It's very easy to come up with this algorithm. And on the other hand, every possible heuristic that you think of for this problem, after a while, you come to believe that cannot beat this, right? I mean, at least I spent you know, some time being frustrated, trying to come up with something that beats this, but I couldn't. And the question is, again, in the analysis, how well does it work? And the answer is that it works poorly, okay? Which is good, because we want to prove lower bounds here. Well, you know, after all, lots of people tried, so we want to prove that those people were not that stupid. Okay, so this has two theorems. So the theorem that we had a theorem that came up earlier this year that proves that if you look at level 4, this requires n to 1/3. Okay, so sides of the clique at least n to the 1/3. Unless it's n to the 1/3, it will fail. This very complex method. At the same time, there was a paper by Meka, Potechi, and Bigderson that proved that if you look at any d, any degree, it fails unless k is n to the 1/d. Okay, and this is up to log factors. Okay, so for the case 4, this is stronger. We just did a much more painful and careful analysis of that case, but this is more general because it looks at every d. Now, these two theorems are based on a certain construction of a witness. So these proofs are based on a construction of a witness and use the same witness that is not the optimal one. Now, I'm used to the fact that, you know, if you are in an exciting topic, there is a couple of papers that come up with similar comparable result at the same time. But here there were 4 papers that come out in the space of a few months, perhaps. So this was in last month there was a paper by Raghavendra and Shram that proved that SOS G4 fails unless k is bigger than n to the 1/2. So this basically closes the gap for the 4th order sum of squares relaxation. So this improves over our result by modifying the witness, but uses happily uses a lot of our lemmas. And then there was a result by Hopkins, Kotari, Potechi here that proved that, again, 4 fails unless k is bigger than square root of n. And then they have an analysis for SOSGD that, again, in this case is not tight, but it improves over the Meka, Potechi, and Bigderson result. So this is a rapidly moving field. Of course, the real conjecture would be that for any degree, this fails unless k is bigger than square root of n over a constant to the d. Now, this is probably without any log factor, probably only with a constant factor. I don't know. Perhaps this will be proved next month. There was an original paper by Meka and Bigderson that proved essentially this result modulo logs, but had a bug. But nevertheless, it's a very important paper, a very beautiful paper, because, not because, but in particular, got me interested into this whole area. And of course, this problem is much less understood than the hidden partition. For the hidden partition, we talked about thresholds up to a factor 2. This, even the leading polynomial factor is open, despite quite some people worked on it. Okay, so since there is some people interested in random matrix theory, there is I want to comment that the key ingredient in this analysis is really random matrix theory, except that it's random matrix theory for some exotic random matrices. So these are random association schemes. Okay, so let me give you a sample example of this type of random matrices. These are not the real ones that matter, but it gives you the flavor of it. Take an Erdős-Rényi random graph, Gn1/2, edge probability 1/2, and then you construct a matrix of sides out of this graph of sides n choose 2 by n choose 2, so indexed by subsets of sides 2. And the way you construct this matrix is the following. You put a 1 every time these two subsets induce a complete bipartite graph, and 0 otherwise, say. The real matrix is a bit different from this, but so this gives a matrix that is a random matrix with highly dependent entries, because it has n squared by n squared entries, but only n random variable. It's not. It's constant sparse, because the probability of this event is a constant. Huh? But so okay. So what you see here is that already the expectation of this matrix is not entirely trivial. It's not like the Erdős-Rényi random graph, where the expectation of the adjacency matrix is just a projector. The expectation here has to do with the symmetry group of the representation of permutation over pairs. Okay. And okay, this you can generalize this matrix to subsets of other sizes, right? And this is what matters really. Okay, just the conclusion. So I think that these kind of ideas that come from theoretical computer science are very interesting to try to understand computational limits to statistical problems. I talked about two uses. One is the hidden partition. In that case, I had the achievability result with simplest level of the hierarchy. And in this case, you can hope to get fairly precise results. In the hidden clique, we had an impossibility result, but as you saw, the situation looks like it's much more challenging. Okay, that's all. Thank you.
I was curious, so like, for say for hidden clique, once you have these random graphs in your analysis, what do you have to do with them? Down to their operator norms, understand their spectra, what do you do to have them?
Once you have the random graph, in the sense you find the
analysis, you said the analysis boils down to analyzing some What about them do you have to analyze?
Yeah, good point. So basically, you construct one for proving the standard witness, the original witness. So basically, this is a witness proof. So you construct an X that has a large value under the null model. Okay, so you construct an object that is feasible and has a large value. So to prove feasibility, you have to prove that a matrix of that type, a random association scheme, is PSD. Okay? And basically, the way this is done is you characterize the spectrum of the expectation, and then you characterize deviation by moment method. And the reason why the moment method makes sense is that you can think of this as a polynomial. The entries of this matrix are polynomials in the entries of the adjacency matrix. So you can think of the adjacency matrix as giving you a bunch of IID random variables, and then you are constructing a larger matrix by constructing polynomials. And moment method is good for dealing with polynomials.